Okay, so today we're going to talk about what happens when a point total or a data point does not fall on the actual standard deviation lines. From now, we're used to saying it's 1, 2, or -1 or -2 standard deviations away, and we're able to find those percents easily. Today, we're going to go a little bit more abstract, and we're not going to land on a nice, even number. And that is common because in the real world, a lot of things don't just add up to be even. They're all over the place, lots of decimals and things like that. So, for instance, in this problem, it says Jeff scored 17 points in last night's basketball game. His point totals are normally distributed with an average of 13 points each game and a standard deviation of 2.5. Would you say he had a typical, a good, or a great game? Explain why and show proof using a normal distribution curve. So first off, we know his point totals are normally distributed. So let's just start by making our curve here. Okay, and with that curve, we put on some lines. And with that curve, okay, we know we're going to have a mean in the middle. And then we're going to have our standard deviations, 3 to the left, 3 to the right. So, according to this, Jeff's average point total is 13. And he has a standard deviation of 2.5. So that means this is going to be 15.5. This is going to be 18. And this is going to be 20.5. This one down here, minus 2.5, that becomes 10.5. This becomes 8. And this becomes 5.5. So this is Jeff's normal distribution for how many points he scores in a game. That's terrible. Okay, so on this night, he scored 17 points. So we're looking at this right here, the 17-point game he had. Well, unfortunately, 17 actually does not fall anywhere on this line that we have for these whole numbers, or these numbers that are on the standard deviations. 17, by our guess, would probably be about right here, if we're estimating. That's what he did that night, okay? So we can't really use our percentages that we were using because those percentages were tied directly to these standard deviation lines and the mean. Now we're kind of in between, but what we can say is that Jeff was right up to here. Now we can't say the exact percentage because we don't have a ZScore table. Eventually we might get one of those and start using that to find the actual scores or the actual percentages. But that doesn't mean we can't do anything with this. What that does mean, though, is that if we look at a typical night, the majority of the time, Jeff is going to be scoring right in here. This is our normal. Most of the data will fall right in here for Jeff every night. He averages 13. Some nights he does a little better. Sometimes he does a little worse. But on average, he's going to be in that green zone. Okay. Then he starts to do a little bit better as we branch out. So in this purple zone, if he's in here, he's usually doing better than what he did most nights. Okay. Or worse, depending on which side of it you're on. If you're scoring lower points, you're not doing as great. If you're doing this more points, you're doing better. And then there's some nights where he's way out here. These are his really good games and his really bad games, meaning that he scores either a low amount. So imagine if he was down here at 6 points. That's not very good if he's averaging 13 a game. Okay? Or if he's up here and he has 20 points, that's super good. It's very rare he does that. It's a great game for him. So we're concentrating, though, on this 17. So we have to ask ourselves, is 17 typical? Is it good or is it great? Well, if we look, we said this is kind of our typical region. Most of the time he's going to score in there. Over here is a good game, or we could say a bad game if it's on that side. And then finally, there's over here, this is where he's doing really great or terrible. And again, it all changes with context on this. So you can see that in our normal distribution curve, even if we're not in that percentage zone that we talked about with the 68, 95, 99 rule, we can still figure out if he's had a typical, a good, or a great game, or bad or terrible, depending on where that curve is and what it's measuring. So our focus today is to figure out, how do I know if that 17 is going to be good? Without even looking at the curve or drawing the curve every time, how can I figure out if 17 is a good thing? And this is where we're going to get into what's called a Z-score. And I mentioned it briefly before with like a Z-score table, but we're just going to focus on finding out a Z-score. And a Z-score basically tells you how many standard deviations away from the mean a data point is. Okay, so we want to figure out how far away, how many standard deviations away are we? Because usually we're used to doing like +1, -2, +2, -3, being right on those lines that we saw up here with those blue numbers. But that, like I said, that's not always going to happen. So we need to be able to figure out, if it's not on those lines, where is it going to be? And how do we measure that? And so we're going to be looking at this thing called Z-score, which is how many standard deviations away from the mean a data point is. And so if we look at it, we want to be able to figure out how far from the mean we are, and then how many standard deviations that is away. So our formula is going to be our data point, which we're going to call x. We're going to subtract that from the mean, because we want to see how far away from the actual mean we are. And then we're going to divide that whole thing by the standard deviation. Because then if I have a difference from the mean and divide by the standard deviation, it's going to tell me how many times our standard deviation goes into that difference. And so again, let's just go ahead and mark this so we understand the formula. This is our mean. This is our standard deviation. And these numbers should always be given to you. And the one thing that changes is going to be right here, because this is a specific data point. Okay? And that's going to give us our Z-score, or tell us how many standard deviations away from the mean a data point is. So let's go back to our original example with Jeff and his basketball game. So Jeff's typical average, we said, was 13 points. His standard deviation was 2.5, according to our data. And on this particular night, Jeff scored 17. That's the data point we're working with. So to find our Z-score, we're going to go Z-score equals 17 minus 13 divided by 2.5. And so we get 4 divided by 2.5. And if we do that on our calculator, we're going to find out that that is 1.8. No, sorry, 1.6. So what we can say here is that Jeff's Z-score for that night is 1.6 standard deviations above the mean. And if you look at that 17 that we did up here and we estimated, that does look like it is one. Let's do that in a different color here. There's one standard deviation. and then about 0.6 standard deviations. So he's at plus 1.6. And that tells us how far away he is. Now, remember that our normal distribution only has 3 standard deviations above or below. So we have to figure out what that means. Well, the typical range for standard deviation, so what we're going to call is our typical or our normal night, is always going to be between, the z-score is going to be between 1, -1, and +1. Okay? A good or a above average, we'll call it that, or again, it could be below average, depending on what we're looking at, is between -2 and -1, or we are between 2 and 1. We're in that next zone. And a great or highly unlikely, we'll say, let's change our tone here. And then we'll say highly unlikely or really rare is when we're between, when the z-score is less than -2, or the z-score is greater than -2. I messed that up. There we go. And so what does that look like? Well, let's just draw a number line here. Here is the mean. 1, 2, 3 standard deviations. 1, 2, 3 standard deviations. So if we were to look at it like we did up there, but in the more general sense, our typical range is going to be here, between -1 and +1. The unlikely range that we're looking at occurs here, in these two spots, where you're just above your typical, but you're not really highly unlikely. It's not in that super rare zone, but that's between -2 and +2. And then finally, we are in the highly unlikely zone. And again, depending on what you're measuring, that may be really good or really bad. And that's that -3 or +3. And again, remember, these number lines go on forever. So anything that is above a 2 or lower than a 2, even if it's way out here, is still highly unlikely. And so that's kind of our z-score measurement right there. When we find our z-score using the formula, we're going to then look at it and say, is this typical, unlikely, or highly unlikely, depending on how far away from the mean we are. And so you're going to be given some practice problems in the next part of this to use just to calculate the z-score and call it typical, unlikely, or highly unlikely. Then we're going to start using them to compare two unlike things to see what you might do. For instance, for colleges, you do ACT tests or SAT. Some people do both. So how do you know what score to send into a college? Which one did you do better on? Because they have very different scoring systems, but you don't want to send in the one that makes you look worse. So there's a way to compare those two things, and that's what we're going to do in our next set of notes after you do a little bit of practice today. So go ahead and do the practice for the z-scores, and then we'll be doing a little bit more notes after that.